Hello, and welcome to the 3.1 Day 1 video. If you looked at the completed notes and you were like, there's so many notes, yes, we are taking this one packet of 3.1 and we're splitting it up into 3 days. So we're taking all that information, doing it in 3 days, so parse it out bit by bit. Anyway, let's get started. So we are focusing on polynomials. So first thing is, what is a polynomial? It's a power function. Where's my pointer? Power function in the form of f of x equal to a sub n times x to the power of n, where a sub n is a real number and n is a non-negative integer. So this is important for what qualifies, for what qualifies as a polynomial and what doesn't. So for instance, x to the power of, I blended those together, negative 2, which is the same as 1 over x squared, not a polynomial. Or if we have something like x to the 2/3, which is the same as the cube root of x squared, this stuff right here, not polynomials. So we're only looking for positive real exponents. And when you're writing these out, please make sure that you are writing them in descending order of power, so that the largest power is first and then it moves on. So I'm going to write that over here. So it should be written in descending order of powers. Okay. So there's a few different things we can glean from a polynomial. The first one is the leading term. So I'm going to highlight that leading term that's right here. And there's a few different things that we can glean from the leading term. The first thing is the degree that's going to come from your leading term. And the degree is just the highest power. And then you're also, from here, going to have your leading coefficient, which I'm just going to shorten to LC because leading coefficient is just, it's very, very long. And that's going to help us determine end behavior. Now, end behavior is which directions are your ends or your arrows going. But you'll notice that end behavior isn't mentioned here. What we do have mentioned, however, is long run behavior. Long run behavior is kind of the more formalized version of end behavior. So let's talk about end behavior and what that is, and then later on I'll talk about how that turns into long run behavior. And long run behavior is mostly just notational. So end behavior is determined by the degree, whether it's even or odd, as well as the leading coefficient, whether that's negative or positive. So I don't know how they're teaching it currently, but I used to teach it in a box. Or in a grid like this and say, okay, we're going to look at the degree, see whether it's even or odd, and then we'll look at the leading coefficient and see whether that's positive or negative. So if we take a look at the examples we already have, this is a positive x squared, so that's an even degree. So that means that our arrows, or our ends, are both going to be pointing up. And then over here, we have a positive x cubed, so 3, that's going to be odd. So it means that my right side over here is going up, and then my left side over here is going down. So that's going to look like this. There's a bunch of stuff happening in the middle. I'm not always going to know, but these ends will always be true. Now for the negative version of each of these, a negative x squared, well, we just dealt with transformations, so we know that if we put a negative in front of a function, it's going to reflect it over the x-axis. So a negative x squared is going to look something like this, with both ends of my function facing downward. So if it's an even degree and a negative leading coefficient, the ends will be facing down. And if it's a odd function, or let's say our cubic, and we reflect that over the x-axis, it's going to look something like this. So this is a negative x cubed, where the left side is facing up and the right side is facing down. So I'm hoping that you learned that at some point. In a little bit, we'll formalize that more just so we can see specifically what that means. Now, as we take a look at all the different functions here, we can see that, oh, we have cubes and we have to the power of fifths and fourths and sixths. It's just showing that all the behavior is mostly the same. It just gets a little bit flatter here. So this red one, the x squared, and just gets flatter and flatter as the degrees goes up, and the same thing over here. Now, we're really only going to be dealing with multiplicities. We'll talk about that in a little bit. Multiplicities of 1, 2, and 3, so you don't have to worry about this specific flatness. Let's move on. I'm going to scroll up. So here we have some general functions. It gives me the degree, the maximum number of zeros, and then the maximum number of terms. So something that I want you to notice here is that if the degree is 2, the maximum number of zeros is 2. Degree is 3, maximum number of zeros is 3. 4 and 4, oh, you can't see me pointing at that anymore. 4 and 4, 5 and 5. So what this really means, and let's make a note, that the maximum number of zeros is the same as the degree. Now, the reason we say the maximum number of zeros as opposed to just the number of zeros is because there can be a whole variety of amount of zeros depending on the transformations. So for instance, right here we can see there's 1, 2 zeros. This is a quadratic, a degree 2 polynomial. But what if this was reflected or shifted up or down? So what if it looks something like this? This is still a degree 2 polynomial. However, now it only has 1 zero. Or what if it was moved up and shifted over to the right? It might look something like this, where it doesn't have any zeros. So that's why we list the maximum number of zeros. And then we also take a look at the turning point. So how many times does it turn around? So here the degree is 2, maximum number of turning points is 1, degree is 3, maximum number of turning points is 2, here it's 5 and 4, here it's 4 and 3. So I'm hoping that you notice that the maximum number of turning points is 1 less than the degree. So that's just how many times does it turn around, and those are highlighted in green. Those are the maximum minimums. We didn't really go over maximum and minimums in our Unit 1 for time's sake, but just letting you know that's something that exists. So let's take a look at those multiplicities, and then we'll go through most of a problem. So here we have something all about multiplicities. So the first thing we have here is a polynomial function of f has a real 0 r if and only if x minus r is a factor of 0. So this is just a statement that needs to be said. I'll let you know that if and only if is something very important in proofs. In college, when I took a proofs class, we called this if-fa-fa because it is shortened to I-F-F. That's not something particularly important you need to know. I just think it's fascinating because I'm a math person and that's what I do. So let's move on to the actual multiplicities. So if you see an even multiplicity, which is like a power of something, an even multiplicity, you notice it says it kind of bounces. It's going to look something like this. So it's going to look like a quadratic, but that's just around that root or around that factor where it's going. Whereas an odd multiplicity, we're only going to be dealing with 2 types of odd multiplicities, multiplicity of 1 or a multiplicity of 3. So a multiplicity of 1, so say we have the factor of x plus 3. If we have a multiplicity of 1, it might look something like this. So if here's 0, 1, 2, 3, you might just have a line going through that. So that's going to look like a straight line. Whereas if we had a multiplicity of, let's say 3, and we're going to use that same factor, it might look like, let's see, 1, 2, 3, something like this, where it looks a little bit more cubic. Some people call this the squiggle. I always learned it as the chair, but just knows that it gets a little flatter around where the specific root is. Take a little bit of time, just a moment for yourself to practice drawing these multiplicities of 3 in both directions. Something that helps me is if I kind of say, here's where my root is, I do half a parabola up, half a parabola down. And so I don't have to do it all one fell swoop. And it's also good to practice in the other direction as well, just in case. So take a moment to do that for yourself. But when we look at the multiplicities, something good about the multiplicities is I now take a look here and I go, okay, so this is now in factored form, not in standard form. How do I find the degree without multiplying everything out? Well, I can look at the multiplicities. So here, if it doesn't say a multiplicity, we assume it's 1. So this is a 1 here and a 1 here. And in order to find the multiplicity, or we have the multiplicities in order to find the degree. Multiplicities, oh my goodness, so many eyes. Multiplicities add up to the degree. So if I take a look at this, I go, okay, this factor has a multiplicity of 1. This factor has a multiplicity of 1. This negative 1/2, that's the leading coefficient. You don't need to worry about that. So 1 plus 1, that is, that is going to give me a degree of 2. So that's what you need. Now, if you read this paragraph for example 1, let me just show you everything it asks us to do. It asks us to graph the polynomial and find the degree, the long-run behavior, maximum number of turning points, the horizontal and vertical intercepts, the zeros, and their multiplicities. What? That is so much information. We're not going to do all of that today. I don't want you to worry about graphing. We're not going to make a table. We're not going to get to that till next video. Right now, we're just going to go through and find all the different features, most of which are pretty quick. And we'll be doing this for this example and one more, and then we'll be done. So as you can see, we've already found the degree. Now remember, this means, since it's an even degree, that both of the ends, oh, that is a highlighter. Oops. That both of the ends are going to face the same direction. And I mentioned earlier the leading coefficient, that's the number out in front, is a negative 1/2. Now since it's negative, it means that both of these ends are going to be facing downward. Now you don't actually have to graph it at this point, but sometimes it helps me just to go through and go, okay, both my ends are probably going to be somewhere down here. And that lets me go through and just remember that. Now, the next thing it asks us to list is the long run behavior. Excuse me if you can hear my stomach, I'm so sorry. So the long run behavior. So the long run behavior is kind of like the end behavior, but we need to use specific notation to describe the directions of these arrows. So I see that my left arrow over here is facing downward. So I'm going to write this as x goes to negative infinity, f of x goes to negative infinity. So that arrow right there, that's me saying goes to. So that's what the arrow means. And then what does this really mean? Well, this means as x decreases, or essentially the left side of the graph, then my f of x, or my y value, decreases. And what that essentially says is that, hey, my left side of the arrow, it's going down. Okay, but what about the right arrow? Well, that's going to be as x goes to positive infinity, f of x goes to negative infinity. Or as x increases, the y value decreases. Now, you don't need the stuff in red, only the stuff in blue. And I know this looks like a lot, but the cool thing is that these x pieces don't ever change. It's always going to be as x goes to negative infinity, and then as x goes to positive infinity. Because that's this left side, and then this right side. The only thing that's going to change is up here. Which direction are the y values going in? If they were going up, that would be positive infinity. But since they're both going down, that's negative infinity. But this is our notation for our long-run behavior. Next, ask for the number of turning points, maximum number of turning points. We're also going to list the maximum number of zeros because that's going to go pretty quick. Oops. So let's see. The maximum number of turns, that's going to be 1 less than the degree, so that's going to be 1. And if we were to list just the maximum number of zeros, that's going to be the same as the degree, so that's going to be 2. And the last 2 things we're going to do is find vertical intercepts and then just information about the horizontal intercepts. So let's see, for our vertical intercepts, actually I'm going to do that over here. So for our vertical intercept, that's our y-intercept. And whenever we want to find a y-intercept, we're just going to plug in 0 for x. So that's going to look like negative 1/2 times 0 minus 2 times 0 plus 4, or negative 1/2 times negative 2 times 4. And that's going to give us 4. Don't leave it here. I do want you to take the extra moment and write it as a point. So 0, 4, there we go. So that's our y-intercept, or vertical intercept. Next, for our horizontal intercept, this one's going to take just a little bit more work because we have some other things to mention as we go through. So for our horizontal intercept, to find our x values, that's when our y value is 0. So this is 0 is equal to negative 1/2 x minus 2 times x plus 4. Oh, okay, that kind of ran into my vertical intercepts, sorry. So I need to know, hey, when is this going to be 0? Well, it's when each of our factors are set equal to 0. So we can say f of x is equal to 0, or the whole equation is equal to 0, when x minus 2 is equal to 0, and x plus 4 is equal to 0. Now, the reason that I write this out is because in the instructions, it asks us to find our zeros and our multiplicities. So when I list our zeros, that's me essentially solving these very short equations I've made. So we have, I accidentally muted myself, sorry. We now have x is equal to 2, and we have x is equal to negative 4. So if we're actually asking what are the horizontal intercepts, and we're going to write these as points, that'll be 2, 0, and negative 4, 0. And the very, very last thing they ask us to find is the multiplicities. If you remember, if nothing is shown, we're going to assume the multiplicity is 1. So the multiplicity of each of these is 1. And you'll notice something I like to do is when I write all this out, I like to just kind of line it up so I can see the information clearly. But these are all the features of a polynomial graph we're going to be taking a look at. Like I said, the actual graphing, we're going to wait to do next video. But let's try one more problem. All right, so for our next problem, we have something slightly longer, so it's graphing this polynomial. With a variety of multiplicities, we can now see that we have a multiplicity here of 2. So let's find the degree. So we have one multiplicity of 2, and then we have 2 other factors that each have a multiplicity of 1. Now remember, to find the degree, you have to add the multiplicities. So 2 plus 1 plus 1 is going to give us a degree of 4, showing that we have an even multiplicity, meaning that the ends of my graph are going to be facing the same direction. And then the leading coefficient, or the number out in front, is 1/4, and that's positive. So even though it's a fraction, it's positive. So both of our ends are going to be facing upward, so something like this. Now, to list out the long run behavior and what that looks like, so we're going to say that as x goes to negative infinity, or just the left arrow, f of x goes to positive infinity, meaning that our left arrow is facing upward. And as x goes to infinity, f of x goes to infinity, which means that our right arrow, or our positive arrow, is going upward as well. So that's all that means. That's the description. Next, we're asked to find the maximum number of turns, and we'll also do the maximum number of zeros. Maximum number of turns is going to be 1 less than the degree, so in this case, 3. And the maximum number of zeros is going to be the same as our degree, which in this case will be 4. Lastly, let's get those intercepts, zeros, and multiplicities. So for our vertical intercept, remember that's when we plug 0 in for x. So we'll have f of 0 is equal to 1/4 times 0 plus 1 squared times 0 plus 2. I think the recording skipped for a moment. Times 0 minus 5, or 1/4 times 1 squared times 2 times -5. That squared is very important. I know it's not going to make a difference right now, but I've seen a lot of people leave that out and then end up messing up their vertical intercepts. Anyway, when we multiply all this together, we get -2.5. It's a decimal. That's totally okay. Please take the extra step and write yourself a point of 0, -2.5. So that is our vertical intercept. And then next, just all the things that come along with horizontal intercepts. So the way we find horizontal intercepts is setting the entire equation equal to 0. So 0 is equal to 1/4 times x plus 1 squared times x plus 2 times x minus 5. And remember, we can say that our entire equation is equal to 0 when either that first factor is equal to 0, or the next one, x plus 2 is equal to 0, or x minus 5 is equal to 0. Maybe it's all of them. We don't know. So when we find our actual zeros, we'll say that, hey, x is equal to -1, and it's going to be equal to -2, and it's going to be equal to a +5. So you can write x is equal to -1, x is equal to -2, and x is equal to 5, or if you line it up like this, that is also okay with me. So when we actually write out our intercepts, when we actually write out our horizontal intercepts, now we write them as points. So that'll be -1, 0, -2, 0, and 5, 0. The last thing we need to find is the multiplicities with all of the i's. So I take a look back here and I see that, all right, we have 2 factors with multiplicity of 1. The other one has a multiplicity of 2. 2, 1, 1. So those are all the features. We're going to get to graphing next unit, or not next unit, next video. Thank you for sticking around. Please go check out that Go Formative.